Hi, welcome to the Office of Undergraduate Research Education Series. Today's session is Environmental Detectives, Collecting Clues About Past Environments by Playing in the Mud. And our speaker is Dr. Andrea Brunelle. And this is a virtual event and it's being recorded. So we ask everyone to mute yourself and turn off your camera to ensure the best experience. And if you have any questions, please use the chat feature or you can unmute when you're invited by the speaker. And this is the event evaluation. We would love everyone to complete that after the session, but we want to remind our Europe and Wilkes scholars that you must complete the evaluation to receive credit for attending today. And the mission of the Office of Undergraduate Research is to facilitate and promote undergraduate, student, faculty, collaborative research, and creative works in all disciplines at the U campus. And we would like to acknowledge that this land, which is named for the Ute tribe, is the traditional and ancestral homeland of the Shoshone, Paiute, Goshute, and Ute tribes. The U recognizes and respects the enduring relationship that exists between many indigenous peoples and their traditional homelands. We respect the sovereign relationship between tribes, states, and the federal government, and we affirm the U's commitment to a partnership with Native nations and urban Indian communities through research, education, and community outreach activities. And now I'd like to introduce Dr. Andrea Brunelle. She's a professor in the geography department.
Thank you so much to Shelley and the Office of Undergraduate Research for inviting me here today. I have a very long relationship with the Office of Undergraduate Research and their amazing UROP and now Wilkes research opportunities for undergraduates. I just love having undergrads in my lab. And as I flip through the various pictures, a lot of the students you see are actually UROP students. So one of the things that we like to talk about when we talk about paleoenvironmental reconstructions is that we are ecosystem detectives. So basically what we're doing is we're collecting sediment cores, which I'll show you in a minute, and then looking at various things that are preserved in these lake or wetland sediments. And these things that we find are basically clues that we then assemble to understand what the past environment looked like for that period of time at that particular place. So paleoenvironmental. Paleo means past, and of course, environment means environment. And this includes a variety of components of the environment, including biological components, geological, hydrological, climatological. And we work a lot with archaeologists to provide paleoenvironmental reconstructions for places where there are significant archaeological remains. So understanding better what the environment was like, what resources were available for people when they were there. The way to start thinking about this is that there are a variety of different environments that we experience. And on the screen, you can see photos of a couple of those. On the left, we have a lodgepole pine forest, something you might see up in the Uintas. And then on the right, we have our classic sagebrush steppe, which you see, all over Utah and Wyoming and the Great Basin. These systems require different conditions in order for them to establish and thrive. You might guess that the pine forest requires cooler temperatures, more moisture, whereas the sagebrush steppe is definitely an arid, high desert type landscape. So when we're looking at our clues, keeping in mind that these two systems are going to leave different clues in our cores for us to look at. We're also very interested in disturbances, so things that have happened on the landscape that can also give us information about what things were like in the past. So disturbances are temporary changes in environmental conditions that create a pronounced change. And examples include fires, floods, windstorms, hurricanes, rapid climate changes, volcanic eruptions, and one of my favorites, insect outbreaks. So, as I mentioned earlier, we take cores, so the mud, sediment cores, and we can collect these sediment cores from any depositional system. And when I say depositional system, what I'm referring to is someplace where sediments and organic materials are accumulating over time. You can imagine that your backyard is not a depositional environment unless you got a leak in your sprinkler or something, right? And there's mud. Depositional environments include lakes, wetlands, springs, bogs, any place where the sediments are continuously wetted. And so things that land on it are then going to be buried by subsequent deposits. So in this image here, I have a lake, and you might be able to tell why I went into science and not art because I made this lovely figure myself. The little yellow balls are pollen. Different vegetation types produce visually different pollen grains. And these pollen grains are released onto the landscape, and the successful ones make it to the female part of that same type of plant, then producing seeds. It's its reproductive mechanism. But what we rely on are the unsuccessful pollen grains, the ones that don't make it to the female reproductive parts of a plant, that just are cast out into the environment. And many of them will end up on the surface of one of these depositional environments, one of these lakes or bogs or whatever. Those pollen grains get saturated with water and then they settle to the bottom. And then as organic materials continually produced in the system and coming from out of the system, we get these layers. And the layers are oldest at the bottom and youngest at the top. So we can get a vegetation record for however long the system. So we get pollen, we also get charcoal, which is the little black dots. When a system burns, as you certainly know, that produces charcoal. And we're interested in charcoal that comes from local fires. And these fires can give us information about, how frequently that system tends to burn, what are the climate conditions associated with fires in this ecosystem, and then how does the system recover from fires? And our records go back tens of thousands of years. And so we can actually examine these processes prior to human modification of an ecosystem, which is a challenge today to make good management decisions based on information that's only from times where the system has already been altered. So we can work with, and we do work with land managers to help better understand how the system functioned under, normal conditions. And then, of course, insects. Insects also can end up in these depositional systems. And one of the insects that we're the most interested in our lab are the bark beetles. So we have mountain pine beetle in the pines. We have engravers in the fir. There's spruce beetles. And so all of these beetles give us information about the disturbance regime, how often are there outbreaks. And in particular, we're very interested in the bark beetles because if you've been to the Uintas lately or, any high elevation forest, you'll notice that there's a lot of red dead trees or just ghost trees, the standing silver trunks. And these are from recent beetle outbreaks. And so one of the questions that we've worked on in my lab is what we're seeing today normal, or is it out of the range of variability? Is it different? And just a spoiler alert here, has not occurred like this in the past. What we're experiencing now with these beetle outbreaks is definitely unprecedented. So is related to changes in climate, environmental conditions, and so on. The oldest sediment, like I said, is at the bottom. And then as layers accumulate, you get to the top, which is the most recent. And then we go out into these systems and we take sediment cores, which is basically jamming a hollow tube into the sediments. And there's a variety of different ways we do that. And then we pull those sediments out. So again, we're taking a stratigraphic in order sediment record where the oldest stuff is on the bottom in the oldest mud at the bottom. And then the most recent pollen will be in those top sediments and then all the time in between. This is Emerald Lake. It's on the Wasatch Plateau. This is a site we've cored actually a few times. And I just wanted to point it out because this site underwent a mortality event from spruce beetles in the 80s that was almost 100%. So almost 100% of the mature spruce on this landscape died during a beetle outbreak in the 80s. And you can still see the ghost forest. So all these silver trees you see that are dead, those were the spruce that were there. And then the live trees that you see were the fir that were growing in the understory. And once the spruce were dead, the fir were like, yay. And so they've grown up. And now, if you go back today, you'll see young spruce coming up in the understory of that fir, trying to regenerate that forest. This is a cienega, which is what we call wetlands in the desert systems. This one is on the Arizona-Mexico border. And you can see that it's a very, very productive system, lots of aquatic plants, lots of grasses. You can see the beautiful cottonwoods and willows that have grown along the edges of it. This is a bog from Range Creek Canyon. Range Creek Canyon is a Fremont Archaeological Research Station that is near Price, Utah. It's a field station for the University of Utah that's run out of the Natural History Museum. An absolutely amazing site. And another example of working with archaeologists. So the site is very important because of the amazing Fremont archaeological remains. And so what we've been doing is coring these squishy spots that occur in the canyon to try to provide some environmental context for what was going on environmentally when the Fremont were there growing corn 1,000 years ago. This is one of the coring devices that we use. It's called a Livingston core. It's about a 2-inch diameter tube, and it's called a piston core. And you can see at the bottom here, this is the piston, and that goes in the bottom of the tube. And so basically what happens is we put the piston in, and then there's a cable that's attached to it. So we pull it up to the top, and then we push the tube down into the sediment. And the reason that there's a piston is to create the suction to hold the mud in, right? Because you can imagine you could jam a hollow tube into the mud, but when you pull that hollow tube out, the mud's gonna, because of suction, is gonna just pull right back out. The piston acts like your thumb on the top of a straw. So probably most of you have stuck a straw in a milkshake. You put your finger over the top of the straw, and you can lift the straw out with the milkshake in the straw. That's what we're doing, but with mud. When we use this particular device, we're usually on lakes, and this is a group of my students going out to our coring platform. That blue raft in the middle is a modified cataraft, 16-foot pontoons, and we anchor that in the middle of the lake, in the deepest part of the lake. And then we use our little shuttlecraft there to go back and forth, and we do our work from that platform that we've stabilized in the middle of the lake. This is a group of students coring in a lake in the Bear River Range. And, you know, this photo was kind of staged, but it really is this much fun. We kind of got stuck out on the lake because our shore crew, who has the little boat that takes us back and forth, they ran off because there were a couple of elk, or no, sorry, not elk, moose in the area that were very interested in what we were doing, interested / annoyed. So we got to spend a little bit of time out on the boat waiting for them to leave. Here we are coring that bog from Range Creek, and you can see again, we're using this Livingston core, and we attach rods to the top of it, which you can see there, so that we can keep pushing it down into the mud. And this particular coring device is all human energy operated. There's no motor, there's nothing mechanized, it's just human strength. And you can see everybody pushing really hard to try to get it down into the mud. The other coring device that we use quite a bit, it's called a vibrocore. And that's what we're setting up for here. And you can see we have this tripod that we set up, because once you get a tube into more dry sediments, it can get pretty hard to pull it out. So we have to set up this tripod and a chain hoist to actually kind of winch it back out once we get it in. So this is a 4-inch diameter aluminum irrigation tube. We sharpen the bottom, we get it set upright, and then it's attached to a cement leveling motor. So when that cement leveling motor is on, it's vibrating like crazy, which helps the tube move down. You can see me and a colleague doing this here in New Mexico. And then this is me, I'm the one laying down. And one of my undergrads, former undergrads and graduate student, Jessica Spencer, and we're creating ballast, right? We're putting weight now on that tube. So it's vibrating like crazy, and we're hanging there from these ropes to give it a little bit of weight to help it jiggle down into the sediments. Sometimes we also have the opportunity to collect samples from a cut bank. So this is again back in the borderlands. We're in the Arizona-Mexico borderlands here. And this stream, which you can see on the left, has been cutting. So in unstable stream systems in the desert, we have what's called arroyo cutting. And what it basically does is as the stream energy comes through, it keeps taking sediment. So the ladder with me on it on the right, pulling these samples, those are wetland sediments that have been exposed because every time a flood comes down that channel, it takes a little bit more of the material. This isn't environmentally ideal, but it gives us an opportunity to get access to sediments we wouldn't necessarily have access to otherwise. And so what we're basically doing here is I have a trowel and little, sciencey Ziploc bags, and you just take in stratigraphic order, just little chunks from the top down to the bottom of these sediments, and we put them in bags, and then we can work on them in the lab.
There is one question. It says,
Okay.
how do you keep gas out of the tube, or maybe you just account for that?
So with the Livingston, it's fully submerged underwater when we're collecting the sediment. So there's no opportunity really for gases to get in. It's the mud that pushes the water that's in the tube out of the way. When we do vibrocoring, it's a hollow tube, and as we vibrate it down in the sediments are just displacing the air that's in the tube. But this is a really good question because we don't have a piston per se for that vibrocore. So once we've hit the bottom, the tube won't go any further. We cut it off near the bottom, near the surface with a hacksaw. And then we pour water in to fill up any empty space. And then we put a cap on it, an airtight cap. So that acts as the thumb on the top of the straw to keep the sediment from pulling out as we are trying to extract it from the sediment. So the core that we were just looking at is a Livingston core. This core here in the tube is from the vibrocore. And so the Livingston tubes, we extrude them on the boat. So we push them out of the tube on the boat. We wrap them in saran wrap and aluminum foil, and we put them into boxes that we make just for this purpose. In the vibrocore situation, it's just one run. We get as much as we can get in that tube, and then we pull that tube out, we seal it up, and we take it back to the lab. And to get the mud out of that tube, we actually have to cut the aluminum tube, and we cut it on both sides, and then we kind of pop it open like a clamshell. So you can see the bottom half here of the tube, and then the top half we've popped off. And so now we can see all the sediments, we can describe them, we can start sampling them in that way. So we get our beautiful mud back to the lab, and we do a variety of tests, and we look for a variety of clues. So the first one I mentioned already, it's charcoal, which comes from fires. And I think I mentioned we look at watershed scale fires, which means we're looking at what we call macroscopic charcoal, which you still need a microscope to look at. But they're pieces that are big enough that because of particle physics, they just don't get entrained in air currents and travel far distance like the smaller pieces do. So we're looking at and counting everything bigger than 125 microns. We do a test called magnetic susceptibility, which measures the ease with which sediments take a magnetic charge. And this really helps us get a handle on potential erosional events. Because you can imagine if you're taking a core out of one of those gooey, algae wetlands, the sediment is largely organic, right? Stuff's living and dying in those wetlands or the lakes, and it's falling to the bottom. So left to its own devices, those sediments are going to be almost completely organic. When you have a fire or just an erosional event in the watershed, the sediments from the slopes, and you can see in this picture here, it's pretty much denuded, and you can see all the evidence here of runoff. When those sediments make it into the lake, they have a different magnetic signal because the terrestrial sediments are derived from bedrock, and bedrock almost always has some magnetic mineral component to it. So if we're looking at our record of magnetic susceptibility from the bottom to the top, and we see two big spikes, We'll then check, like with our fire record, were there fires at that time? Is that an erosional event associated with the denuding of a landscape, right? Like we can see in this picture. You can imagine how that would be a vulnerable landscape to erosion. Yeah, we can also have, just big flooding events that bring in material down like tributary streams and whatnot. It gives us a good idea of this erosional history, which can relate to fire and or climate events. And then, of course, like pollen. These are my favorite. Uh, Even if you look at the very beginning, we have the pine forest and the sagebrush forest. Those two systems have very different vegetation types and accordingly very different looking pollen grains. So this guy up here in the upper left is sagebrush, one of my favorites. The one over here to the right is called is Mormon tea. This guy here on the left, spiny one, that's from the sunflower family. On the right, you have grasses and so on. And so by looking at the pollen that is present in the different layers of the sediment, we can see when a system might shift from a forest to a grassland or a grassland to a sagebrush steppe or whatever, because these changes in pollen will tell us what plants there were, and we can see the transitions over time. So just putting these clues all together on one page, more pictures of pollen. These aren't the beetles. These are some other interesting little ants that we found in the Cienega, the desert wetland samples. And it's an ant that is exclusively known to occur in these wetland environments. So we, in addition to, the sediments being organic, we also were able to find these evidence of these organisms that would only be there if it was still in that condition at the time that they lived there. So again, this is back to that slide. We have the pollen types that are associated with it, pine and spruce. And then on the right, we have our sagebrush, dandelions, ragweed, things like that. So it's very different. The assemblages are very different, and it's really easy to see these changes in the sediments over time. So this is just a schematic that we put together to kind of help understand. So in this top beige, darker beige section, for example, these are pine grains, right? So it makes sense because this is a place we coordinate. It's currently a pine forest. So we'd be a little worried if there wasn't pine pollen in the surface sediments. As we go down a little deeper in that lighter color, the vegetation shifts from the pine to sagebrush. So before it became a pine system, it was a sagebrush steppe. These charcoal layers indicate fires. And then we can see these shifts back and forth between environmental types. And that's another really interesting thing about fire is, as I mentioned at the beginning, understanding how an ecosystem responds to fire, what's its recovery pathway, how does that work in these systems before they were modified by humans is really important, again, for developing management plans, right? Knowing how systems have recovered in the past can help us build resilience and the ability to restore today. Another really cool thing that we can do with these environmental clues is forensics. And there's a whole field called forensic palynology, which is using pollen from evidence from various, crime scenes or other, places where we have questions about things. We can use the pollen to help us ask questions. One example of this, and a colleague of mine did a lot of forensic palynology for the FBI at his lab in Texas before he retired. And one of the projects he told us about was they had someone who they suspected of committing a crime, and they collected, the shoes and clothing from this person's home as part of the evidence. And they sent those materials to my colleague, and he was able to determine that this person had been in a spruce forest. That's the pollen that was embedded in the mud that was stuck in the treads of the shoes, which corresponded to where they had found, unfortunately, the body, in this case, of, the person against whom the crime had been committed. So they were actually able to use this evidence to document that the person who they suspected had actually been in the same place where they had found their evidence. So that's kind of neat. There's another line of palynology or pollen analysis that looks at honey. And in this case, there's like a whole group of people who make sure that if you buy clover honey, it's actually from clover. And the way they do that is they look at the pollen residues that are in the honey. So if that honey is full of grass pollen, then we know that it's not from, the clover. And it's become a standard testing protocol for honey companies to have their honey tested. This was a neat project. We had someone reach out to us, just a civilian who was wanting to buy this vehicle that had this history of, where it had been and races it had been in and all these things. And he wanted to see if there's any way we could verify that. And there was mud caked in the underbody of the vehicle. And so the question was, is there any evidence that this vehicle had been in Hawaii, which was part of its, history? So we took some of those samples of mud and we looked at them, and things we were looking for are the type of plants you might find, only in Hawaii. Fortunately, we didn't find anything that was only unique to Hawaii, so we weren't able to help him confirm. But again, kind of a neat application. So what I'd like to do now is just take you through one of our projects. And this one is from desert wetlands. This one is a cienega, a desert wetland. It's up in the mountains of Baja California. And you can see in the distance here, let me see my cursor, that little puddle right there. That's the wetland we were coring. But I like this picture because it shows you what the extent of this wetland has been in the recent history. This kind of grayish green vegetation we see around the further edges is sagebrush, and sagebrush doesn't like wet feet. So if the ground is saturated for any amount of time, the sagebrush can't survive. And so what we could determine was the extent of this wetland at its maximum saturation, because there's just no sagebrush there. And then once you get past that edge, then the sagebrush is present, and you can move up then into the forested systems as you move away. These wetlands that we look at in the borderlands, this is just the US-Mexico border, and all the little blue sites are places where we have records. And one of the first projects I did in the desert Southwest was working with a land manager from the San Bernardino National Wildlife Refuge. It's near Douglas, Arizona, and it's right on the border. And these wetlands are home to a wide variety of native and endangered plants and animals. And so the wildlife manager was very interested in understanding the vegetation history, pre-modification, because the landscape's definitely been modified today. And also the role of fire, because before we did this work, there were about 6 different studies or papers that talked about fire in these desert systems. And basically, they all said something different about what the fire regime should be. And as he was developing these management plans, he wanted to have some information about, what really has happened in the past with fire, so that he could apply the appropriate fire strategy to these wetlands that he was working on restoring and conserving. And then we're also interested in the climate controls on these wetland systems. So when you're in the Southwest, this is actually pretty simple as far as climate goes. There's really 2 main climate systems that affect this geographical area. One is the summer monsoon, which you can see in the upper left-hand corner, lovely lightning strike there in the Sonoran Desert. And then in the lower right picture, what you see is a big spring bloom of annual flowers that come up after a wet winter. And wet winters in the Southwest are caused by El Nino events. So when you have an El Nino winter, lots of precipitation, then you tend to get these amazing wildflower displays that spring. These wildflowers are beautiful, but they're also important for maintaining fire in the desert because they create a fine fuel. If these flowers weren't here, if we were looking at this in, September, it would just be, dirt, bush, dirt, cactus, dirt. There's not much connecting the different plants, except for when you have these super blooms, these spring blooms of flowers that came because you had such a wet winter. So you can really only carry a fire in these systems if you have the fine fuels between the bigger vegetation to connect the fire and allow the fire to move. This is just an image of El Nino and how that works. And it's basically the sloshing of warm surface water in the Pacific to the west coast of largely South America, but also, into Central America and the southwestern US. And this is the footprint of El Nino. So living in Utah, if you're in Utah, you know that we have had really impressive El Nino events. I think it was either 87, 88, or 88, 89. I can't remember that winter where there was a massive El Nino. And it was such a powerful El Nino, it made it from its core area down here, kind of in the Four Corners region, all the way up here to Salt Lake City, where you can see the little outline of the Great Salt Lake. So really strong events can have impacts further north than what we're seeing here, but they always affect this borderlands region where we're working. This figure is looking at these El Nino events and this record. So we have on the y-axis events per 100 years, and this is referring to El Nino events per 100 years. So 0 at the bottom and 40 at the top. And then on the x-axis, we have time. So present is over here on the left and, 10,000 plus years to the right. So as these peaks and troughs occur, it's telling you when there's more El Nino events, when the curve is higher. And when there are fewer events, you can see that it's very close to the bottom. So what this study proposed was that ENSO was pretty quiet coming out of the last ice age and didn't really start having a significant impact on these desert landscapes until about 5,000 years ago or so. And you can see that pretty distinct change from very quiet El Nino to active El Nino, where it's going across this threshold that's called the ENSO band. Once you get above that, then you see enough El Nino activity that you can really start talking about El Nino. And ENSO is the El Nino Southern Oscillation, which is the whole system. So these are the data from that core we took at the San Bernardino National Wildlife Refuge. And there's kind of a lot going on here, so I'm going to step you through it. So again, we have time on the y-axis. So the year we took the core, which was 2005, is at the top. And then we have about 8,000 years ago at the bottom. So this record covers the last 8,000 years. This first panel that you see here on the left is the El Nino events. It's that same panel I showed you in the previous diagram, but I've just tipped it up on its end. Paleoecologists tend to think of time with present at the top and the oldest at the bottom because that's how it deposits in these systems, right? So it's not your traditional timeline where time is on the x-axis. We do them a little differently. The second panel here is the preservation index from the pollen that we found in these cores. And the preservation index is important because pollen is a really unusual substance. The shell of the pollen, which is what we find when we extract pollen from the mud, is actually a protein shell. And this protein shell, it's called sporopollenin, is really unique because it preserves beautifully for hundreds of thousands of years if it stays wet, if it stays in an anoxic environment. It oxidizes really fast, so if it's out where it's exposed to the air, it doesn't last very long at all. But as it's deposited in these settings, those wet sediments preserve it. Now, if you have wet sediments that dry out for a while, and then they get wet again, and then they dry out, the pollen doesn't look so good. It's sort of like if you had a wrench, right? And you left it out in the backyard and it got wet and then it got dry and then it got wet and then it got dry. It's going to rust, right? Oxidize much faster than one that's either just in a bucket of water or in your toolbox where it's not getting wet at all. So a low preservation index tells us that the sediments were not consistently wet the entire time. So in this earliest part of the record, where we don't have a lot of ENSO events, El Nino events, we don't have very good pollen preservation. And this is important because these desert wetlands are charged by winter precipitation. So the snow that falls in the mountains during these El Nino events, as it melts, it goes down and it recharges the groundwater, which then emerges somewhere else in these spring settings. So if you're not getting the winter snow, you're not going to have an active spring. And if you don't have an active spring, any of the pollen that was deposited isn't going to preserve very well. So we're able to use this evidence of poor preservation as an indicator of the system drying out. And then on the far right here, we have the charcoal accumulation, which is just how much charcoal did we find in the sediments. And you can see that we basically didn't find any until about 5,000 years ago. And I have to tell you, this was the first core we worked on from this environment, this project. And I was starting to get nervous because the student who was working with me started counting from the bottom and was working to the top, and she wasn't finding anything. And we kind of thought it might be a bust. But then all of a sudden, you can see there's lots of charcoal. And this charcoal shows up when we see the onset of ENSO, El Nino activity, because those El Nino events are creating winter snow that then recharge the groundwater, which then allows water to emerge at the surface at the spring. So early in the record, we don't have fine fuels either, right? If you don't have winter precipitation, you're not going to get that beautiful spring bloom of fine little, flowers and little grasses and stuff, right? You're not going to get that. And if you don't have that, even if you have ignition with the monsoons and the lightning in the summer, there's just nothing to carry a fire. You can have a lightning bolt hit a saguaro cactus and it can burst into flames. But if there's no fuel around the base of that cactus, the fire is going to end there. And so that's what we saw happening. We saw evidence of intermittently wet surfaces because of the low pollen preservation. We enter that El Nino phase. We start seeing pollen being preserved because the sediments are staying wet. During the same time, we see the increase in fire, the winter precipitation, creating those fine fuels. There's this quiet phase of El Nino, which we attribute to this low preservation phase. The quiet phase of El Nino happens before preservation, but in a lot of environmental and climatic systems, we will see a lag between what happens and when it's actually recorded. And then we have super active ENSO for the last, couple thousand years. You can see that pollen preservation is beautiful, and we go back to having an active fire system. And this was really helpful for Bill, the wildlife refuge manager who we were working with, because he could better understand how fires happened and that they did happen, that fires do occur in desert systems. But it takes these fine fuels in order to allow them to spread across the landscape. Okay, so the things we learned from this study was that the preservation ratio is an indicator of sediment moisture, which in this system leads us to understand about El Nino, the El Nino Southern Oscillation. This has been really helpful because as our research has moved to new areas, we're doing a lot of work in the West Desert with the Dugway archaeologists. And we were actually able to use the same preservation ratio that we developed for the southwestern deserts in the West Desert of Utah, because it's the same thing. When those springs dry out, the preservation ratio goes down, and it allows us to understand better the amount of effective moisture that might be available. That fire in these fuel limited systems is very closely tied to El Nino. You have to have winter precipitation to have those little flowers that are then going to dry out to move fire from one place to another. The length of the record gives us information on El Nino because you have to have groundwater for the springs to initiate. So we know that that didn't happen in this system until about 8,000 years ago. When you're doing research, you don't want to get circular, which means you don't want to say this happened and so this happened, and then go back to what your evidence was and then attribute that. You want to make sure that your lines of reasoning are linear. So based on what we're learning or what we've learned, we're actually able to start going backwards and understand El Nino from the sediments instead of using this existing El Nino record to tell us what's going on in the system. So why do we care? I mean, let's be truthful. A lot of people like playing in the mud, myself very much included. But what are we learning? And again, like I mentioned, this Southwestern research was very, very tightly linked to restoration. And here we have a couple of my graduate students. They're standing on the edge of one of these arroyo cuts. And just a few days, a week before we got to the field site, there had been a big flood. And you can see how brown, how chocolatey this water looks. That's because it's cutting. We call it hungry water because it's able to pick up these sediments and continue cutting the stream down. These wetlands, when they're working, actually slow down flood pulses and allow sediment to accumulate. But because of the loss of vegetation cover from grazing and other land modification activities that the Euro-Americans undertook when they got to the Southwest, the systems were destabilized. And so we see these massive downcuts and the deterioration of these spring systems. We have two pictures here. The upper right one is called Los Ojitos. It's one of the cienagas we worked on. And this site was barren and horrible looking, just about, I think it was like 8 years. And what they did, what they started doing as to help restore these wetlands was they put, they call them gabions, but they're basically like little check dams across the streams so that as a flood pulse comes down, these check dams slow the water. And as the water slows, it drops the sediment. And once the sediment is dropped and it has this amazing vegetation buffer, we actually get the restoration of the wetlands of these springs. So this picture in the upper right was a disaster less than 10 years before we took this picture. But by slowing the water down, it started depositing sediment and it became an active spring, which is an amazing resource for, plants and animals that live in the area. And then this lower left picture is just meant to show you what streams in these desert systems are meant to look like. And then, of course, fire, right? Fire has a role in these systems, and we understand it so much better now. This isn't the desert. This, just to, let you know I'm cheating here. This is actually a burn in Minnesota. Oh, okay. So this is what I was looking for. So this is Los Ojitos. It was actually 5 years. So they put the check dam in 5 years before I took this picture. And this is what it looks like after only 5 years of having that water slowed down and depositing material. So we have data for restoration, understanding the role of fire, but also resilience, understanding El Nino, what's happening now and what's happening in the future, because, whether we like it or not, climate is changing and El Nino is going to change too. I'll take questions. And if you don't have any, I think we have a few queued up here. Okay, so one of the questions that was phoned in ahead of time was, how do sediment cores compared to ice cores from glaciers? Do they give similar information and are used for different environments? They're definitely used for different environments, right? In order to take an ice core from a glacier, you have to have a glacier or an ice sheet, which is very different than the Southwest. But a lot of really important environmental information can come from ice cores. There are some beautiful, highly resolved ice cores from like the Andes, high elevation tropical locations where there's lots of ice, and then they're basically just freezing the pollen. It's like putting, your frozen broccoli that's in your freezer, right? If it's frozen, it stays for quite a long time. The same thing happens with pollen. If it falls on the ice, it gets captured in the next layer of snow and then becomes part of the ice. So we can get pollen from ice. Ice cores are amazing for isotope studies, which can give us information about past climate. Um, Unfortunately, we're losing our glacial and ice sheet records as they're melting. We're losing time. Um, but luckily, we also have had amazing ice core scholars collect ice cores from around the world that are now in very carefully protected facilities so that we still can look back on those, even if the modern location isn't there anymore. This one was hard. What is the most interesting finding found through this research? I get pretty excited about a lot of it. This whole idea of El Nino, um, I'm just obsessed with El Nino and how it shows up so many ways in so many systems and how important it is to the ecosystem form. You know, what does the system look like? Function? Are there fires? So I love El Nino. The bark beetle work has been really fascinating, depressing, but fascinating. Um, I just love working with undergraduates in the lab and teaching them how to do this. I don't know that that's necessarily the most interesting part, but it's definitely the most exciting and what I find to be the most fun. The methods that we use in the lab, a lot of them are really old. People have been looking at pollen for, over 100 years. Um, Charcoal, again, it really started becoming a paleoecological tool, gosh, when I was working on my master's, so think about it, 30 years ago. But today we're doing some really interesting things. I have an undergraduate or Wilkes scholar in my lab right now pulling mud samples to send to a fossil DNA lab in Denmark. And so we're looking for human mammoth, who was on the landscape 10,000 years ago. So that's definitely cutting edge. We're also using XRF, which is X-ray fluorescence, which gives us elemental composition of the cores, which also can help us understand erosion and climate. Um, yeah, so we have some very time-tested methods, but we're still expanding. Like right now, that student is doing something that we've never done before in our lab. And then ethical concerns in environmental research, not so much with what we do because we're really working with, fossil plant remains. When our research intersects with archaeology, we have to be much more careful to be respectful and follow, the ethical guidelines that are laid out for archaeology in our country. So, that's where we really have to start paying more attention and being more careful. Let's see, what are the foundational questions that still need answering? I think probably the most pressing question and maybe the most difficult is taking what we've learned and applying it to a landscape that no longer looks the way it did before, climate change started really impacting those systems. But then also finding a way to make it applicable to the changes we see coming. So really thinking ahead about how do we protect, restore, make various ecosystems more resilient in the light of current and future climate change.
One additional question, Andrea, from a registrant, it says, does our era show up in the mud?
Yes, it does. Yeah. Our era shows up in a variety of different ways. So when the Euro-Americans showed up, they brought stuff with them from, Europe and other places. So we see some really interesting plant markers in the sediments. One of my students right now is working in a sagebrush system in New Mexico, and she can see when or is it that one? No, 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 no. Maybe it's the Bear River Project. We can see Russian olive show up in the record. So Russian olive is an introduced species, and it's showing up in the record. It's not there, it's not there, not there, and then it shows up. And we see that a lot with, different introduced taxa and at different times. We can see the impacts of fire suppression. Fortunately, we see a lot of evidence of different types of pollutants. Um, yeah, so we can very easily see, recent things. One of our students in the lab, she has a core from the Northern Rockies, and I believe it's a fire that happened in 2013 that we can see the big fire peak, the big charcoal peak.
There's one final question in the chat. It says, how does your research get peer reviewed? Like, how can they exactly reproduce your work?
That is an excellent question. Yeah. So, we follow the same, when we're publishing, we follow the same peer review guidelines as, any other scientific journal outlet would be. But you're right, we can't necessarily reproduce, someone can't reproduce exactly what we've done without basically doing the entire study over again, which is, expensive and very time consuming. I'm sure you can imagine that counting pollen and charcoal sometimes takes, years, depending on how many sites you're looking at and whatnot. So it's not necessarily that the actual data we collect are reproduced. It's more the interpretation, we have to be very explicit in the methods we use, in the chemical processes we use, like to extract the pollen from the sediments. Analytical approaches are scrutinized quite closely, including like things like looking at our radiocarbon dating that we use to, figure out what happened when. So, it is different in that you can't go into a lab and over the course of a week or two or a month, you can't reproduce what we did. But the data that we present are very carefully scrutinized by the reviewers and then also compared to other research in other places to look for inconsistencies that aren't explained, um, by our interpretations.
Well, thank you very much, Andrea. We appreciate this very, very interesting presentation. I just want to remind everyone about the evaluation form. I'm putting the link in the chat right now. The Europe and Wilkes scholars must complete this in order to receive credit for attending today. And I just want to remind everybody, the Office of Undergraduate Research, we're in the Sill Center, which is just east of the Union. We're open Monday through Friday, 8 to 5. Our website is our.utah.edu, or you can email us at our@utah.edu. And thank you again, Dr. Brunelle. We truly appreciate this presentation today.
Yeah, well, again, a big thanks to the Office of Undergraduate Research. I've just, one of the best things about my entire career here at the University of Utah has been working with so many undergraduate researchers in the lab.